Okay, so coming into today, you were supposed to have watched the video of Stacks Days One, and everything that was good about it is in the Gaddis book, and that's about it. Well, this is where the NIOF book is going to start to kick in and help us out a little bit. And the reason what I'm saying here is we're going to see how to use some of these things. So let's take a look at, first of all, what is Stacks? And from that video, you should have gotten everything I put on here. You're going, yep, 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 and yep. All right. I did give you for today all of the code listings for chapter 19. So you're going to be able to access the files for Stacks. And then next week, when we do queues, it's also going to be in chapter 19. Two pretty big topics. The video of Stacks talked about LIFO. The last one in is the first one out. And it's still popular today. The ever popular Pez dispenser, you put one in and you push it down and put another one in and push it down. And then when you pop the guy's head, one of them pops out and you get to eat the Pez dispenser. And so it's the last one in is the first one out. A lot of times in grocery stores, you see they're in the backside adding new things, but it, they're doing it the wrong way. The last one in is the first out. They just keep pushing it. All right. So we're going to take a look at this LIFO concept two ways. From the video, you got, again, we're going to repeat this process. Learn a topic. How does it go with arrays? How does it go with linked lists? And through discussion, your notes should have come up with when I push to the end. And when I pop from the end. Those two words, push and pop, are familiar. You saw those last semester when there was conversation about vectors. Okay. But there's lots of reasons why we use linked list instead of vectors. Much easier to work with. Hi. Oh, hey, Corinne. So push to the end and pop to the end. We needed to make sure we had a count so we could go to that location. We would check if it's empty, if that count became zero. Again, we had all of our functions. A new function is push. That was instead of add. Pop instead of delete. We could still keep track of is empty. We would need to have is full, that's for sure. The other way you looked at a stack is with a linked list. This time we are pushing to the beginning, which was kind of nice because we had code like new nodes next gets the value of head, head gets the value of new node. And then when we popped, we said head gets the value of heads next. So head would jump to the next one in the list. So these were both the same. Push to the end, pop from the end, push to the beginning, pop from the beginning. In the code listings and what you would have seen in the book for Stacks, you will see that our specification and implementation files are called int stack. And then for the linked list, they were dynamic int stack. So are there any questions on what you see before you? You're coming into class, you're armed with all this stuff, you're ready to use it and become experts. Going once, going twice. Sold to the lady in the second row. All right, so let's first of all take a look at one of two math type concepts we're going to use today. And we're going to say, oh, this is actually kind of cool. And we can write the code using stacks to take care of this. All right. First thing, if I said to you, some of you had this, probably not, but may have had this in a high school course. Some of you may have seen some of this in discrete structures. We're going to do this, convert from base 10 to base 2 using a stack. So here's what it's going to look like. All right. So I'm going to set up a long division. 2, 23. And now I'm going to ask you, how many times does 2 go into 23? Integer division. How many times does 2 go into 23?
11.
11 times. What's the remainder?
1.
Good. 2 goes into 11 how many times?
5,
Remainder?
1,
2 goes into 5 how many times?
2.
Twice. Remainder? 1. 2 goes into 2 how many times?
1.
Once. With a remainder of,
0.
yeah. 2 goes into 1 how many times?
0
With the
with a
remainder of
remainder of
1.
1.
Okay. I kept pushing. Push, 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 push. Now I'm going to pop. Pop. 1, 0, 1, 1, 1. And we just converted. Did we mess up somewhere? 2 is 11 is 5. I did mess up. Goes this way. 1, 0, 1, 1, 1. So I'm going to pop the remainders. Another way to look at them is, what if I did them this way? 1, 1, 1, 0, 1. And I popped and wrote the 1. Popped, displayed the 0. Popped, displayed the 1. Pop, pop, pop. So I'm able to get this. 1, 2, 4, 8, 16. 16 plus 4 plus 2 plus 1. So that's going to give me an answer in converting. When it's not given, it's a 10, base 10 to base 2. Anybody come across this yet? Somewhere in their life? Base 10 to base 2? No? Well, what did I do here? Let's see. I have a number, right? The number equals 23. And then I got into a while loop and I went until my number was 0. Let's see. What did I do? I
You divide the num by base,
I divided the num, and then what did I do? I divided it, and then
and then you take the remainder and pop it.
okay. So what? Not pop it, but I'm going to push it on the stack. So I'm going to write this. This is why I'm doing pencil today. Num equals num divided by 2. So that gives me the 11. But now I wanted to push the remainder. Uh-oh. I need to move this down because I need the remainder first before I divide by 2 to keep going. So I'm going to do something like this, where I'm going to say push. What would I like to push first?
Num and the module
Excellent.
of
Num mod 2. I'm going to push the remainder on, then I divide by 2, and I'm going to keep going. Thanks. And then I probably should count how many there are so that I can have a nice little for loop that goes from 0 or 1 to count. Again, I'm using pseudocode here. 1 to count, where I pop the remainder and I don't know, some sort of display. Good? Yeah? No? Would this work with another base? What if I said let's convert da-da, 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 da-da. I want to keep this separate. There's my nice block of code in my notes. Yeah, what if I said convert 100 in base 10 to base 4? Well, it's going to be a couple of digits here. I don't know how many. Just going to scribble out 4. Will the same concept work? Well, let's see. 4 goes into 100. Well, that really stinks, doesn't it? Let's not use 100. That's a bad example. Huh. How about base 8? Instead of base 4, let's make this base 8. Base 8. 8 goes into 100 how many times?
12.
12. With a remainder of
4.
4. 8 goes into 12 how many times? How many 8s in 12?
1.
Yeah. With a remainder of 4. How many 8s in 1?
0.
0 with a remainder of 1. Then we start 1, 4, 4, base 8. 100 base 10 is 144 base 8. So now we have some test data. What I'm going to do is go and share. Let's see. Share. I don't want that screen. Share. Dude, I can't see this. I need to stop sharing for a second. My apologies. Now I can share. Boom. So I gave you a code listing, a code samples is what it's called, chapter 7. And if you take a look at it, it looks something like this. Okay. So what I'm going to do is give you a little bit of time, and I want you to go get, this is going to do conversion from base 10 to base 2. Everything is done in 2s. You can put in our test data of 23 to make sure it works, and then do a quick modification, changing the 2s to 4, or you could do an input of what base would you like to convert it to, kind of deal, so that the user can input what it is. Now, if I look at this program, it needs stack.h. And stack.h should be in the code listing files that I already gave you today, except it's not called stack.h, it's called int stack. So Gaddis calls it int stack. The NIOF book calls it stack. Okay, just to keep them straight. It's in stack is the one I gave you, and you can use that. You just have to modify this slightly. But I'm going to put you in groups and have you go and get this program up and running. Questions? I'm going to start. So the second part today, we're going to do this kind of, I don't even know what those words mean, infix to postfix. expression tree representation, an expression tree. All right. Well, first of all, what is an expression? And you've had enough math courses. You should know that A plus B is an expression. I have to leave and rejoin my audio. Okay. So A plus B is a simple expression. And when the operator is inside, we call this infix. Now, what we're doing today in with this expression tree seems kind of okay, and we're using it for stacks. But the second half of this course, we're going to be doing lots and lots of stuff with trees. So what you see right now is an infix expression, A plus B. Now we're going to represent this as a tree, and the tree is going to look something like A plus B. A plus B. Now, starting to get into some lingo, some terms. This guy right here is a node, okay? But we're just going to call him node. This guy is the left, and this guy is the right. In fact, it's the left child and the right child. And this is a tree. Okay. So now all of a sudden I have what's called an expression tree. And when I refer to a node, the plus, A is to the left, B is to the right. Just some simple basics. We're going to hear some terms as we go through the semester, including subtree. We just mentioned a node, like this is a node. Technically, this is a node and this is a node. Edges. Edges are what connects nodes. We have parents and we have children. Okay, the parent would be the plus, the children would be AB. But we're going to look at these trees lots and lots and lots of different ways. Okay, so here's something called infix. The operator is in the middle of the expression. What else do we have? We have something called prefix. That's when the operator comes before the two terms. Well, if we have pre, believe it or not, we have postfix AB plus. Okay. So if we're all good with that, I want to come over here. And when we refer to something that's an infix tree, we go A plus B, left node right. Something you'll get really good at as we go. Prefix. Prefix. That looks like it's the node first, then the left and the right. So we're going to represent this node left to right. And postfix, left, right, and then the node. All building blocks right now. Understand this to be able to look at this to get to here, because this is going to become important, that order. So let's take an expression a little bit bigger than A plus B. Let's put it into an expression tree, and then let's see what we got, and then we're going to see how this works with stacks. So I'm going to start with something as simple as A times B plus C. Which operation comes first?
Multiplying.
Multiplying. Okay, multiplying. So this is going to get done first, and then this is going to get done second. So if I look at this and I say, all right, I want to make this postfix. Now the order AB is AB is AB is going to be ABC. The only thing that moves are the operators. So if I want postfix, I'm going to go AB times, because that's what's done first. And then this whole thing got added to C. So this whole thing, C plus. How about prefix? Prefix. Once again, this gets done first times AB, and then that gets added to C. So the plus actually goes in the front. Let's try another example. How about this one? A times B plus C. Yeah, when we have our infix, we have to deal with parentheses quite a bit. What is this in postfix? What is this in prefix? Somebody have a guess for the postfix?
Um, A, is there like the asterisk? Or, um, oh, yeah, it actually, A asterisk BC plus.
Okay. So this gets done first. So what would that look like? Well,
Oh,
there's, go ahead.
BC plus, and then A asterisk.
How about A here, asterisk there? This gets done first, so that's my BC plus. So think of that as blah. Now I have A times blah, so it's going to be A blah with the operator on the end. So BC plus gets done, BC plus, that becomes a thing, A times all of that. Yeah, this is one of those light switches. Once it goes on, it's like, oh, I think I got it now. This guy gets done first, plus BC times A. Plus BC gets done first, so that becomes a unit. Then I move this operator in front of the first thing that gets multiplied times the second thing that gets multiplied. That being the second thing. Can we do one more? Well, sure. Anytime somebody asks to do one more, I will gladly do one more. 4 plus 2 times 8 slash 6 minus 4 and another parenthesis. First of all, what does that equal? What does the, yeah,
10.
10? That's 2, that's 4, this is multiplication, not plus.
12 then. Wait,
That's 2. 8 divided by 2 is 4.
oh,
That's 6.
Is it
yeah,
24?
24.
Yeah, I think I get 24 as well. Okay. Excluding that part, that's just for later. That's just for later. Write this as postfix. I need to first go through and say, this one gets done first. This would be second. This would be third. And this would be fourth kind of deal. You could argue that and say, this can be done first, that can be done second and third. So why don't we do that? Let's go with, it's not gonna matter which way we do it. We'll do this second and then this third. Postfix. So this is gonna be 4, 2 plus. Over here, this is gonna be 6, 4 minus. Now I have 8 and blah. So 8 blah divide. 8 blah divide. Then this first whole thing and this second whole thing multiply. Questions? Okay. Let's go with this now. A nice big stack. If I see a number, I push. Push 4. Push 2. Operator. Operator says pop, pop, and add. I'm going to pop the 2. I'm going to pop the 4, and I'm going to add. Now, if you notice, I put the 2 to the right and the 4 to the left. Because if I had 4 minus 2, that would be the order I would want. The 4 is on the left. So the first one pop to the right, pop to the left. I add them. I just popped this. I popped this. I added them and pushed the 6 back on top. Push 8. Push 6. Push 4. Pop. Pop 4. Pop 6. And subtract. The answer I get is 2. The next number I see is divide. Pop 2 to the right, pop 8 to the left, and divide. I get 4. I pop the 2, I pop the 8, I push the 4. Now I hit multiply. Pop the 4. Yeah, first one goes on the right. I popped the 4, I popped the 6, and I multiplied, and I got 24. Drop the pen. What? So by having postfix, whenever there's a number, I push it. When there's an operator, I do pop to the right, pop to the left, add. Pop to the right, pop to the left, subtract. Pop to the right, pop. And after I pop, and perform the operation, I pushed it back on. Kind of cool? Maybe. Share. Conversion from base 10 to base 2. There's stack.h, stack.cpp. Remember, if we're using Gaddis, we use the int stack. But let's see, there's the dynamic stack. Again, this is NIOF's version instead of DYN like we saw before. And if I get down a little farther, I'm going to see converting infix to postfix. converting infix to postfix. So you have a program right now that does amazing stuff, working from left to right. If it's a space, do nothing. Left brace, something's going to happen. A right brace, plus multiply, plus minus multiply, divide, and mod all come in here the same and do something. And then if it's just a regular number, check out this for loop. That's to get you into a loop that you're going to get out of with a break. Instead of using a while loop with a true and false or something like that. So what I'm going to do is put you back into groups. You're going to be on your own. When you're done, we're done. But you're going to get that code that I just gave you, which I think is really cool. You are going to input parentheses 4 plus 2 parentheses times da 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 da, and you should get output of this. You notice we have to work with all single digit numbers. It's not that elaborate. But we're going to convert infix to postfix. And you have test data. You have more test data up here. If you do this, does it come out to be that?